So we're going to talk about conservation of momentum, and we know that momentum, which is a vector, is equal to mass times velocity. And suppose you have two astronauts out in space pushing on each other, then each, suppose this is A and this is B, this B will push A with the force A, and A will push B with the force B. And what happens is that the sum of all the forces, Fa plus Fb, okay, is equal to 0, because they are equal and opposite according to Newton's third law. So these are called internal forces. And so if I take the sum of, if I just look at the internal forces, I find that the total force is 0. So in other words, sum of all the forces internal, okay, so we're only talking about, in this case of internal, is equal to 0, and therefore the change in momentum over change in time is 0, which means that momentum p, the derivative of p is 0, momentum p is a constant. In other words, p doesn't change. For example, to elaborate, okay, to make it much more clear, Fa by Newton's second law is dpa by dt plus dpb by dt. And this is 0, and if this is 0, that's 0. Okay, now we're talking of just internal forces. I'll get to the external forces, all right? And which further I can write d total momentum, Pa, plus Pb, right, is 0, which means that Pa plus Pb is a constant. It doesn't change. That means the total momentum does not change. So the total momentum of the two astronauts does not change. Okay. The total momentum of the two astronauts does not change. So we call that conservation of momentum. All right. Now, this is not only true, suppose this, in general, I can write, if the sum of the external forces, okay, is equal to 0, we know that the internal forces cancel out. Okay? If the sum of the external forces is equal to 0, then the change in momentum with time also is 0. Then the total momentum if the sum of the external forces are 0, then the total momentum does not change. In other words, the total momentum remains a constant. Okay, so we're going to apply this conservation of momentum to collisions. So when two things collide, you have a collision. Right? Two cars collide, you have a collision. Or a car hits a wall, you have a collision. Okay? We're going to apply conservation of momentum to collisions. Right. For example, if you have an object A that has a head-on collision with object B, okay, we're going to do one-dimensional collisions, okay, and we're only going to talk about head-on collision, right? What happens when they interact, when they collide, right? The forces that act, all right, cancel out. In other words, the net force is zero. And therefore, I can say that the total momentum before and after, so they collide and they bounce off, okay? If I call this velocity of A1 and this velocity of B1, this is velocity of A2 and velocity of B2. One is before and two is after. And what we find is the forces, the interactive forces in a collision are equal and opposite. And if we ignore the external forces, the collision forces generally are large enough that we can ignore the external forces. And if we can ignore the external forces, okay, we know Newton's second law, sum of the external forces, okay, changes the momentum. Okay? So this is zero because the collision forces are large enough, and of course the collision forces also cancel out each other. So the net force is zero. So on the right hand side, if I take the external as well as internal forces, everything here is zero, which means that the momentum is a constant. The total momentum of the system does not change. Momentum of the system does not change. So we find that in any collision, okay, momentum is conserved, okay, because the collision forces are large enough that we can ignore the external forces, right? So if the external forces are zero and the internal forces are zero, the total force on the left-hand side is zero, and therefore the change in momentum with time is zero. There's no change in momentum with time. In other words, dp by dt is zero, which means the momentum does not change. Momentum remains a constant because the derivative of a constant is zero. So I can say that the total momentum of the system remains the same. So in any collision, the total momentum before collision is equal to the total momentum after collision. Okay. So the next thing we are going to talk about, there are two kinds of collision. Okay. The first is elastic, and the second is inelastic. Let me give you an example of an elastic collision. Elastic collisions generally occur for example, suppose an object collides with another object, right? You can think of a spring, for example, in an ideal spring. Suppose you have an ideal spring, right? And let's say an object collides with this moving object, collides with this ideal spring. What will happen is that the spring will compress and this will bounce back with the same speed, right? So the kinetic energy before and after are the same, right? So we call that an elastic collision. So elastic collision the total kinetic energy just before collision is equal to the total kinetic energy just after collision. In real life, in the atomic world, collisions, head-on collisions are generally elastic, or we assume that they are elastic. In the macroscopic world, you can think of, let's say, a 6 ball on a pool table colliding with an 8 ball, right? That collision is approximately elastic. Okay, we can think of the two objects, they're rigid enough that whatever kinetic energy that they have before collision is equal to the kinetic energy immediately after. Okay, you can think of they deform slightly like a spring and then they bounce back. So the energy before, the kinetic energy before and the kinetic energy after are the same. Okay. Inelastic collision the total kinetic energy is not conserved. Okay. Inelastic collision. Okay. The total kinetic energy before is not equal to the total kinetic energy after. Okay. Remember, momentum is always conserved in any collision. The total momentum just before collision is equal to the total momentum just after collision, okay, in both elastic and inelastic. Only in elastic collisions do we find that kinetic energy is conserved. In an inelastic collision, the kinetic energy before is not equal to the total kinetic energy after, because some of that energy is lost when two objects collide, and that energy shows up as heat. Okay, so when two objects collide, if you had a sensitive thermometer, you would find that the two objects are slightly warmer. In other words, the molecules that make up these objects now speed up. All right, and it shows up, that energy shows up as heat. Now there's one particular case of an inelastic collision wherein when two objects collide, they stick together, and we call it a perfectly inelastic collision. So perfectly inelastic collision is one where the two colliding objects stick together. In other words, the relative velocity after collision is zero because they stick, right? So let's talk about, let me give you an example of an inelastic, perfectly inelastic collision. Suppose you have an object that's, let's say this is 2 kilograms moving at 3 meters per second, and let's say this is 4 kilograms moving at 5 meters per second. All right? So, obviously this one will overtake this one and eventually they will stick together, right? Somewhere they will collide and let's say they stick together, right? What is the velocity of this object? Okay, what is the velocity with which they would move? Okay, so let's try to solve this. We know that the total kinetic energy before collision is always equal to the total kinetic energy just after collision, right? Whether the collision is elastic or inelastic, this is a perfectly inelastic collision, right? So what's the total momentum? 5 times 4, mass times velocity is the momentum. Remember, momentum is equal to mass times velocity. So the momentum of this is 20 kilogram meters per second. And it's in that direction plus 6 kilogram meters per second. And therefore the total momentum before is 26 kilograms meters per second. And hence the total momentum after is also 26 kilograms meters per second, right? Because the total momentum before and after are going to be the same. Okay, conservation of momentum. Okay, because we are ignoring the outside forces and the internal forces cancel each other out. So the net force is 0 and hence the momentum has to be a constant, right? So what is the momentum here? The total mass is 4 plus 2, which is 6, okay, kilograms times V. So we know that the momentum of this should be 6 times V, and hence V, the velocity, is 26 kilograms meters per second divided by 6 kilograms. So kilograms and kilograms cancel out, and you have 6 divided by 26. Okay, I'm sorry, 26 divided by 6, and you have 4.333, 4 and 1/3. 4.3 repeating meters per second. Okay, so that would be the velocity with which they would go. And of course, if you multiply 6 with 4.3, you're going to get 26. If you multiply 6 with 4.3, you're going to get 26. So the total momentum before and after are the same. What we find is that even though this is an inelastic collision, and if you were to compute the energy, the total kinetic energy before and the total kinetic energy after, you will find that they are not the same, right? So let's try to find, so this is the total momentum before. Let's find the total kinetic energy before collision and after collision, right? So I know the velocity here. The velocity is 4.3 repeating, okay, meters per second. So I'm going to erase that, right? So what's the total kinetic energy before? How do you find the kinetic energy? Remember, kinetic energy is equal to 1/2 mv squared, So if I take the kinetic energy of this, half mass, which is 4 kilograms, okay, this is the momentum, right? Velocity squared, 5 meters per second squared, okay, plus 1/2, 2 kilograms, okay, 3 meters per second squared. So what do you get? The total, I'm sorry, I shouldn't have. So this is, 4 kilograms, 2 kilograms, they're stuck together and they move with the velocity of 4.3 meters per second repeating, all right? So what is the total kinetic energy before? 25, half of 4 is 2, 2 times 25, that's 50 joules, right? Energy is measured in joules, okay? 25 times 2, which is 50, plus, what's this number? So this, let me write it up. So this is 50 joules. What is this? 9, right? This 2 and 2 cancels out, 3 times 3 is 9 joules. So the total kinetic energy here is 59 joules. Okay. What about here? What is the total kinetic energy after? Right? So again, 1/2, what's the mass? 6 kilograms, right? Times 4.3 repeating squared, right? So if I were to square that, okay, times 3, half of 6 is 3, so times 3, I get 56.3 joules. Okay, so yeah, so you get 56.3 joules. 3 joules repeating. Okay, so you can see the kinetic energies are not the same. Okay, in fact, it has lost about 2.7 joules of energy in the collision. And whereas the 2 joules of energy gone in that collision, okay, if we can ignore friction, that energy would have, these two surfaces would have heated in colliding. And if we had a sensitive thermometer, we could actually calculate that 2.7 joules would have gone as heat, okay, because these surfaces would be warmer after collision than before collision. Okay. In general, suppose if I just give this numbers, instead of numbers, if I just put, this is mass of A, this is mass of B. I'm going to assume, to make it easy, that B is stationary. Okay, and this is moving with the velocity VA. Okay, and VB is 0. Okay, so this is before collision, and then they collide. Okay, this is MA, MB, they collide. Okay, and let's say after collision they have a velocity V, right? So let's find, so we know from conservation of momentum, the total momentum before, which is, okay, conservation of momentum. The total momentum before, which is ma A times VA is equal to the total momentum after, which is MA plus MB times V. Okay. Let's apply conservation of kinetic energy. Okay. I'm sorry. So what is, I take that back. So what is the kinetic energy before collision? The kinetic energy before collision is 1/2 MA VA squared. That is 0, right? So this is the total kinetic energy before collision. Okay, this is before. What's the kinetic energy after collision? It's 1/2 mass right times V squared, right, velocity squared. All right. Okay, let's see how this compares to that. All right, we know that if I were to solve for this, the velocity is equal to MA VA over MA plus MB. Okay, if I were to solve for V. And if I put this V back here, right? So I'm going to erase this. Okay, so if I put this back here, what do you get? The total kinetic energy after. This, by the way, is kinetic energy after. So kinetic energy after is equal to 1/2 MA plus MB, right? And the velocity after is given by, from conservation of momentum, it's MA VA over MA plus MB, right? And this is squared. See, it's squared. So I have to square that, and square that, right? So this will divide out with one of them, right? And so what are you left with? You're left with 1/2. Okay, I can write this. Okay, I can rewrite this in this manner, right? I can take one of the MAs out, and what remains here is MA plus MB, right? And I can write it this way, 1/2, right? I've already taken one MA there, so I have an MA, right? And this is VA squared, right? So you get the same thing. If you multiply this, you get this squared, you get that squared, and this, of course, this would, one of the MA plus MBs would cancel out, and you have the factor half. But what is this? This is the total kinetic energy before. So what you get here is kinetic energy after is equal to MA over MA plus MB, and this is the kinetic energy before. And you can see that the kinetic energy after is less than the kinetic energy before, because this number is a fraction. It's less than 1. MA divided by MA plus MB is less than 1. And hence, the kinetic energy before is greater than the kinetic energy after, which, okay, because this is an inelastic collision. So I've just shown that the kinetic energy is not conserved for inelastic, completely inelastic collisions. But it's true for any inelastic collisions, not just completely, perfectly inelastic collision. Okay, it's true for any inelastic collision. But so the thing you should remember is that momentum in any collision, be it elastic or inelastic, is always conserved. Kinetic energy is only conserved in an elastic collision. So let's talk a little more about elastic collisions, and then we'll do some problems. All right. Suppose you have a object, mass ma, okay, moving with the velocity va1. This is before. Okay, and there is mass mb, and this moves with the velocity vb1, right? And then they collide. Okay, and what you have here what you have here is after. Two is after. Okay, so after collision, these are the velocities. Okay, so we have two principles. One is conservation of momentum. So let's write the conservation of momentum. The total momentum before is what? Is equal to the total momentum after, which is ma va1. Okay, let me write it here. ma va1 plus, I think I'll run out of room. Let me see. Let me write it here, right? This is before, this is after. So conservation of momentum, I'm going to write it here. ma va1 plus mb vb1, right, is equal to the total momentum after collision, which is ma va2 plus mb vb2, right? So momentum is always conserved. So we're talking of a specific kind of collision here. We're talking of elastic collision. All right. So what we have here, in an elastic collision, momentum is conserved. Total momentum before is equal to the total momentum after. We also know that the total kinetic energy before and after are the same. The total kinetic energy before is equal to the total kinetic energy after. So if I write the kinetic energy, I get ma va1, 1/2 ma va1 squared plus 1/2 mb vb1 squared is equal to 1/2 ma va2 squared plus 1/2 mb vb2 squared. Okay, and again I'm going to run out of room, so I'm going to take these diagrams off. You know what they mean. So total kinetic energy before collision is equal to the total kinetic energy after collision. We are talking of elastic collisions. Okay, just before and after. So the total momentum before is equal to the total momentum after, right? So if I rearrange this, right? If I rearrange this, by the way, halves will cancel off, right? And I'm going to get all the A's on one side. Okay, I'm going to get all the A's. So if I rewrite this, I get mass of A, okay, and this would be VA1 squared, right? If I bring this over on this side, that's MA minus, right? That becomes minus VA2 squared, right? On the other side, okay, if I take this, I'm going to take all the B's on the other side. So you get MB, okay? If I take this on this side, okay, VB1 squared, and of course it's going to be a minus, right? If I take that on that side. And this, if it's in the bracket, it's going to be VB2 squared. Okay, because minus and minus will give you that plus. All right. So I'm going to, let me call this 1, right? This equation 1, right? What about this equation? If I rewrite it, I can write it in the same manner, except it's going to be VA1 minus VA2, right? If I bring this on this side, and if I take this on that side, I'll get minus MB VB1 minus VB2. Okay, I'm going to call this 2. So if I divide 1 by 2, so if I divide this by this, of course, think of it, right? If you divide it, this will cancel off, right? MAs will cancel off. And what you have is VA1 squared minus VA2 squared divided by VA1 minus VA2. Okay, that divided by, these will cancel out. This will cancel out, right? MBs and the minuses will cancel out. On the other side, you have VB1 squared minus VB2 squared divided by VB1 minus VB2. Right, we're almost there. And would we come now this is the difference of two squares, so I can write this as VA1 plus VA2, the top, VA1 minus VA2 divided by VA1 minus VA2, and on the other side the same thing, VB1 minus VB2 times VB1 plus VB2, right? And this is VB1 minus VB2, right? So this and this will cancel off, this and this will cancel off. And so what you're left with is VA1 plus VA2, right, is equal to VB1 plus VB2. Right? Now if I bring, I'm going to rearrange it so I get the relative velocities before and after. So I'm going to bring all the ones on one side, so you get VA1 minus VB1, right? Bring this on this side, is equal to, okay, minus, you get VB2, right? And if I bring that will be minus VA2, which I can write as VA1 minus VB1 is equal to, all right, I'm going to put a minus sign here, VA2 minus VB2, right? So what is this? What are these terms, right? What do they mean? This one, just remember, velocity of A1, right, is with respect to the ground. Okay, this is velocity of B1 with respect to the ground, right? And right, if I put that minus sign, even though it's implied, okay, these two are all with respect to the table or the ground, right? I can write this as VA1 with respect to the ground, and this, remember relative velocities, I can write it as V ground with respect to B1, which is the velocity of A1 with respect to B1, okay, as measured by B1, right? So the velocity, the relative velocity as measured by B, in other words, so this is the, so what we see here is the velocity of A as measured by B, right? So on the left hand side you have velocity of A1 as measured by B1 is equal to the negative of the velocity of A2 as measured by B2. Okay, what it means is that the velocity before collision and the velocity after collision are the same. So this equation tells you that the velocity before and after this are the same except the sign is reversed. So the total velocity before collision, the relative velocity before collision is equal to the negative of the relative velocity after collision, right? In numbers, what does that mean? For example, suppose you have an object, okay, let me take, let's say this is moving at 4 meters per second, all right? So in an elastic collision, and this is moving, let's say, at 2 meters per second, okay? So what is the velocity? Suppose you're standing here, with what speed would you see this object approach you? Okay, or in other words, what is the velocity of, I'll call this A, I'll call this B, and you're standing here, okay? What's the velocity of A as measured by B before collision? So before is 1, right? So this is velocity of A as measured by the ground plus the velocity of the ground as measured by B. Okay, so this is before. So what is the velocity of A as measured by the ground? It's 4 meters per second, right? What's the velocity of B as measured by the ground? Okay, the velocity of B as measured by the ground is -2. Okay, so the velocity of the ground as measured by B would be +2 meters per second, which is 6 meters per second, right? Does that make sense? So if you're standing here, you would see this object coming towards you with a speed of 6 meters per second. In other words, simply put, okay, in 1 second, this will move 4 meters. In that same 1 second, this guy would have moved 2 meters. Can you see? From your perspective, this has come closer to you, right? The gap between you has reduced by 6 meters in 1 second, right? What happens after they collide in an elastic collision? After they collide, let's say, I'm just picking out numbers, okay? Suppose this is 1 meter per second, okay? And this is the smaller one, let's say it bounces with the speed of 5 meters per second, okay? What is the velocity after collision? So velocity of A measured by B, 2 is after, okay, is equal to the velocity of A2 with respect to the ground plus the velocity of the ground with respect to B2. Okay, so velocity of A with respect to the ground is minus 1 meter per second. Velocity of the ground, okay, with respect to B2 would be the negative. See, this is the velocity of B2 with respect to the ground. So the velocity of, and this is the velocity of B1, 1 is before with respect to the ground. This is the velocity of A1 with respect to the ground. This is the velocity of A1, A2 with respect to the ground, right? So velocity of A2 with respect to the ground is equal to 2 meters per second. Velocity of B2 with respect to the ground, but we want velocity of the ground with respect to B2, that would be minus 5 meters per second. So which is what? Minus 6 meters per second. So can you see the two velocities are equal and opposite in elastic collision? Okay, so you'll see this object come towards you at 6 and it'll hit you and go away at 6, right? In other words, and that's obvious, right? In 1 second, this guy would have moved how far? 1 meter. In that same 1 second, this guy would have moved how far? 5 meters, right? Can you see the gap from your perspective, from the perspective of B, right? You, because you have moved 5 and he has moved 1, from your perspective, this guy has gone in the negative direction by 6 meters. He has moved away from you by how many? By 6 meters in that direction. So that's the minus, okay? So what I'm trying to say is that the velocity, the relative velocity before collision is equal to the negative of the relative velocities after collision. Okay, so this is the relative velocity before is equal to the negative of the relative velocity after. So in an elastic collision, so I can write, right? The speeds are the same. That's 6, that's 6. The speeds are the same. In an elastic collision, the relative speed before, I'm not talking about velocity. The velocities are opposite. The relative speed before and after are the same, right? So we're going to use this fact in many of the elastic collision problems, all right? So two things we are going to use. One is conservation of momentum, ma va1 plus mb vb1. Total momentum before is equal to total momentum after. And we're also going to use that the relative velocities before is equal and opposite to the relative velocity after. So the relative velocity va1 minus vb1, relative velocity before collision, is equal to the negative of the relative velocity after collision. Okay, so we're going to use these two facts to solve many of the collision problems. So let's say per second. So in this collision problem, suppose you have a 4 kilogram block. Moving to the right at 6 meters per second. Right? Collides with a 2 kilogram block moving at 3 meters per second. so this is VA1, VB1. Okay, this is A, this is B, all right? And after they collide, all right, after they collide, so I'm going to draw this diagram here, 4 kilograms. With what speed would it move? Okay, so there are two unknowns. This is VA2, 2 is after, right? And this is VB2. So we want to find the velocities immediately after collision. So this is before, this is after. So simple problem like that. Okay, so we are going to use these two principles to find the answers. Remember, there are two unknowns, so I need two equations, and I have those two equations. The first equation, if I use principles of conservation of energy, what is that? 4 times 6, right? MAVA1, which is what? 24 kilogram meters per second, right? That's that velocity going in that direction, or whatever direction. Yeah, right? Plus. What is this? 2 times 3, which is 6 kilogram meters per second, right? So what's the total momentum before? Okay, that is 30 kilogram meters per second, right? That way, in the positive direction. So that's this number. This is that, and the total is 30. So from conservation of momentum, I know that this total momentum before should equal the total momentum after. So I know that this before, right, which is 30 kilogram meters per second, is equal to that, right? And MA is 4 kilograms and MB is 2 kilograms. So, right? Okay, so I have one equation there. Okay, the second equation, what is the relative velocity before? So the relative velocity before should equal the relative velocity after. VA1 is 6, right? And this is plus 6, right? Minus, that is 3 meters per second. So what is the relative velocity after, right? So the relative velocity before. What is the relative velocity before? It is 6 minus 3, which is 3 meters per second, is equal to the relative velocity after. So I don't know. So now I have two equations. That's one and this one, right? So I have two equations. One is 30 kilogram meters per second is equal to 4 kilograms VA2 plus 2 kilograms VB2, right? And the second equation, 3 meters per second is equal to minus VA2, right? Minus VA2 plus VB2, right? So if I solve them simultaneously, right? What if so let me write this over, let me rewrite this. This is minus VA2. So this is minus VA2, and this minus and minus is plus VB2, right? So what I'm going to do, I'm going to get rid of 1, right? Simple simultaneous equation. So let me get rid of this. So I'm going to multiply throughout by minus 2. So I'm going to multiply throughout. So this will be minus 2, both sides by minus 2, right? So minus and minus, that will become a plus. So if I multiply this by, so this will become minus 2 times 3 will become what? Minus 6. Okay, this will become plus 2. Okay, minus and plus, and this will become minus 2. Right? So what do you get? If I add these two equations, right, this will cancel off, right? So I multiplied both sides by 2 kilograms, right? This is kilogram meters per second. I multiply both sides by minus 2 kilograms, right? So this is what you get. So 30 minus 6 is 24 kilogram meters per second, right, is equal to plus 2 and minus 2 cancels off. So what do you get here? 6 kilogram meters per second. 6 kilograms times VA2. So if I solve for VA2, I get VA2 is equal to 24 divided by 6, right? So that'll be 4 meters per second. And it's plus. So VA2 is 4 meters per second. Okay? Kilograms and kilograms will cancel off. Okay, so that's one. What happens if I plug this back into this equation, right? One of the equations. If I plug it back here, let me do it here. So you have minus 6 kilogram meters per second is equal to 2 kilograms, right? And that is what? VA2 is 4 meters per second plus minus 2 kilograms times VB2, okay? So if I solve for this, this is minus 6 kilogram meters per second. This is equal to 8 kilogram meters per second minus 2 kilograms times VB2. All right. So if I subtract 8 from both sides, what do you get? Subtract 8, so you get 6 minus 8 is minus 14. Okay, kilogram meters per second is equal to minus 2 kilograms times VB2, and therefore VB2, okay, kilograms and kilograms cancel out, that minus and minus is equal to 7 meters per second. Okay, so the velocity of B2 after collision, so you have two answers. Velocity of A after collision. Okay, so after collision, this 4 kilogram block will move with the velocity of 4 meters per second, and this 2 kilogram block will move with the velocity of 7 meters per second. And that makes sense. The smaller one will bounce off with a larger velocity, right? What are the relative velocities? So just to check, what is the relative velocity before, right? It is VA1 minus VB1, right? So VA1 is 6, okay, minus VB1 is 3. So the relative velocity before is 3 meters per second, okay? What are the relative velocities after? Just to check. So this is VA2 minus VB2. VA2 is minus 4 meters per second because it's going that way, right? Minus, okay? So this is VB2, right? Is going to the right. That is plus 7. I'm sorry. This was a minus, this was plus, okay? That's my fault. So it's 4 meters per second, and this is minus, this is plus 7. So this is 4, and this is 7, okay? Both are plus because they're both going to the right. So what do you get? Right? That's correct, right? In an elastic collision, before, the speed before is 3, the speed after is 3. The velocities are equal. This is 3 meters per second, are equal and opposite. So this is 3 meters per second, and this is minus 3 meters per second. Okay? All right. So just remember, when you're working problems in elastic collisions, you have two equations, MA1 VA1 plus MB1 VB1 MB, right, is equal to mass of A okay, well, this is 1 is before, 2 is after. So you have two objects, mass A and mass B collide. Momentum is conserved. Momentum is conserved no matter what, whether the collision is elastic or inelastic. Okay? Only in elastic collision does the velocities, the relative velocity before, which is VA1 minus VB1, is equal to the negative of the relative velocity after collision, which is VA2 minus VB2. 2 is after. Okay, so you can only use this in elastic collisions. This you can use it for both elastic as well as inelastic, right? So these are the two equations you will need to solve for problems in elastic collisions. Okay, because generally you'll have two unknowns. You'll have this. You'll be asked to find this and this. Okay, so you have two equations to help you solve that. Okay, the next thing we're going to talk about is center of mass. Right? So center of mass. Right? So if you have two particles, or n number of particles, m1, right, at a distance of, say, this is my coordinate system, this is my 0 centimeters, m1 is at a distance of x1, and then there's m2 at a distance of x2, right, and then maybe there's an m3 here at a distance of x3. So we can find the center of mass. This is how we define the center of mass. Okay, it's the weighted average, the mass average, right? So I'm going to call this x, center of mass, is equal to m1 x1 plus m2 x2 plus dot dot dot. Let's say there are n number of particles. Okay, so I've just shown 3 of them, but suppose you have n number of particles, right, divided by the total mass, which is m1 plus m2 plus dot 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 plus mn, right? And this, of course, is the total mass, m. So I'm going to call the total mass m, right? So I can write in short, the center of mass is equal to summation of mi xi divided by the total mass. Okay. suppose these were not distributed in one line, they were distributed all over the place. You had x1, you had x, y, and z. Then the center of mass can be found. Okay, y center of mass is equal to summation of mi yi divided by the total mass, and the z center of mass is equal to so you have three equations. And we know that R, center of mass, which is X center of mass times I plus the Y center of mass times J plus the Z center of mass times K hat. Okay, so in 3 dimensions, this would be true. And of course, if you rewrite this, you could also write it this way. The R center of mass, this is divided by the total mass. The R center of mass, you can write it as M1 R1, right? These are all vectors, by the way. These are just numbers, okay? Plus M2 R2 plus dot 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 Mn Rn, and the whole thing divided by the total mass, okay, in 3 dimensions. So that will give you the center of mass. So what exactly is, for example, the center of mass, right? Suppose I want to find where the center of, suppose I have 2 masses. Let's say this is 2 kilograms and this is 1 kilogram. And this is separated by a distance of 3 meters, right? Where is the center of mass? Where is the balance point, so to speak, right? So if I take this as X, this is my starting point, my coordinate system. 0 centimeters is here, and this is 3 centimeters. If I want to find where the center of mass is between the line joining the 2 centers, I need to find X center of mass, right? This is M1. So M1 is 2 kilograms, right? M1 times, we are just talking about X, X1, which is of course 0 centimeters plus 1 kilogram, M2. 1 kilogram times the what is the X coordinate? 3 centimeters divided by the total mass. What's the total mass? 3 kilograms. So what do you get? 1 kilogram, 2 kilograms times 0 is 0. 1 kilogram times 3 is 3 kilogram meters divided by 3 kilograms. So you get 1 meter. So the center of mass from here would be 1 meter away. Can you see this is the balance point? Because 2 kilograms times 1 is equal to, what is, if this is 1 and this is 3, this will be 2, right? So 2 times 1 is 2. This is 1. 1 times 2 is 2. Okay, so this would be the center of mass, right? If there were 2 stars, for example, that were orbiting each other, they would orbit, not, this wouldn't go around the 2 kilograms. I mean, 2 objects, not stars. Stars are much bigger, right? But suppose there were 2 stars, large objects. One had twice the mass of the other. Then they would go around the center of mass. In other words, sometimes later this is going to be around here and this is going to be up there, right? So they would go around the common center of mass. So this object, the bigger object would make a smaller circle, the other one would make a larger circle. Okay, so they would orbit each other around the center of masses. Okay, so that is the center of mass. We can also write, if I take the derivative, so let's go here. You know that the x center of mass is equal to m1 x1 plus m2 x2 plus mn xn divided by the total mass. Okay, if I take the derivative of this, by the way, I can bring this m up here, dx by dt is equal to m1 dx1 by dt plus m2 dx2 by dt plus mn dxn by dt, which gives me m, this is v center of mass, is equal to m1 v1 plus m2 v2 plus mn vn. And what is this? This is the total momentum of all the particles. So suppose you have a number of particles, m1, right? And they're all moving, okay? So this is the total momentum. m1 v1 is the momentum of the first particle. m2 v2 is the momentum of the second particle. So suppose you have all these particles. This is moving with a velocity v1, this is moving with the velocity v2, v3, v4, and so on, right? So this is the total momentum. Okay. So total momentum is equivalent to the same thing as taking the velocity of the center of mass and multiplying it by the total mass. All right? So the total momentum of a system of particles, okay, moving, can be reduced to taking the mass, the total mass, and multiplying it by the velocity of the center of mass. Now we have seen that if there are no outside forces, okay, now remember, as these particles, if I look at the whole system, you have internal forces, which of course will cancel out by Newton's third law. If there are no outside forces, then I know that the total momentum is conserved. Okay, so if there are no outside forces, this number doesn't change. So what does that mean? That means the total mass times V center of mass is a constant. So if there are no external forces, okay, then the total momentum is conserved, does not change. Okay, so if there are no external forces, the total momentum is conserved. This number doesn't change, which implies, I'm going to write that here, which implies okay, that this value remains the same. M times V center of mass is unchanged. In other words, this doesn't change. So V center of mass okay, moves at a constant velocity. What does that mean? For example, if there are no outside forces, right? Suppose you have a wrench in space that's, thrown and it is spinning. So you have this wrench, as good as I can draw a wrench. Okay, or on a table, okay, I throw this wrench. So even though this wrench is spinning as it's thrown, right, okay, the center of mass is generally closer to the larger end. This center of mass will move at a constant speed as the spinning. So all the particles are spinning, right? Eventually this is going to be somewhere here, right? And that is going to be over there, right? And okay. So this wrench is spinning, right? But the center of mass, okay, if there are no outside forces, the center of mass will continue to move at a constant speed. It will move, right, equal lengths and equal time, right? So the velocity of the center of mass moves at a constant speed. Further, I know that mv, center of mass, is equal to m1 v1, right, in the x direction. This is in general, okay, x, y, and z, m2 v2, okay, plus dot 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 plus mn vn, right? Now earlier I had said dx by dt as v center of mass. It's actually v center of mass, the x coordinate. I forgot to mention that. I should have also done the same thing for the y coordinate. Y center of mass times dt is equal to the v center of mass, okay, in the y direction, okay, and dz center of mass by dt is equal to v center of mass in the z direction. So, and then when you combine the three, you get this, okay, and of course this is the total momentum. Now if I take the derivative of that, I get m. So this will be a vector. These are all vectors, all right? These are just numbers. So m, if I take the derivative of that, derivative of the velocity is acceleration. So I can write m times a center of mass is equal to m1 a1 plus m2 a2 plus dot 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 plus mn an, right? So an example of this is, suppose you have a projectile, right, that shoots out, right, and somewhere along its path it breaks up into two pieces, okay, one piece goes that way and the other piece goes that way, the heavier piece, right, or whatever. Okay, so this projectile breaks up into two pieces. One goes this way, whoops, okay, and the other one goes that way. Okay, so even though they follow different trajectories, the center of mass, right? Now here, there is gravity, so it's accelerating, right? Gravitational acceleration. So even though individually they have different forces, subjected to different forces, okay, the center of mass will follow the original path. Okay, it behaves as if, okay, this thing, if it had unexploded, it would have taken this route. So even though these pieces, it has broken up into a million pieces, the center of mass will still follow the original trajectory. Okay. So if this doesn't change, right, this quantity will follow the original trajectory, right? So each is subjected to the force of gravity. Each accelerates as it goes up. Okay, so one more thing that I want to talk about is the center of mass systems. So if you're given V center of mass, we know that V center of mass is M1. Okay, suppose you have two objects. One is MA. All right, so this is MA, and the other one is MB, and they collide. Okay, the center of mass of this collision can be written as MA X1, V1. Yeah, this has VA1 plus MB VB1. Okay, so this is the velocity of the center of mass. All right. So I can find the velocity of the center of mass of two objects that are moving towards each other or moving in the same direction. I can find the velocity of the center of mass, how fast it is going. If I know this velocity and if I know this velocity of the center of mass reference frame. Center of mass reference frame. So suppose you have an object MA, and the center of mass reference frame simplifies a lot of collision problems. If you shift the reference frame to the center of mass, we find the center of mass, we shift the reference frame there, right? So suppose you have in the original frame of reference, MA is moving with the velocity VA1, okay, and MB is moving with the velocity VB1, right? And of course, after collision, we want to find VA2 and VB2. That's the whole objective, okay? This is in the original, so this is the velocity in the original frame of reference. This is the velocity of B in the original frame of reference. If I want to find the frame of reference, the velocity in the velocity of the center of mass in the original frame of reference, so this is the velocity, okay, of the center of mass in the original frame of reference. Okay, velocity of the center of mass in the original frame of reference. Okay, I can write V center of mass, right, is equal to MA VA1 plus MB VB1 divided by the total mass, which is MA plus MB, right? That's the total mass. Now, let's say I shift the frame of reference to the center of mass point. So I shift the frame of reference, the original frame of reference, okay, to the center of mass. In the new frame of reference, the velocities would change. The velocity of, I'm going to call the velocity in the new center of mass. So wherever that center of mass is, okay, I'm going to call this U1, and let's say UA1. And this MA, this is mass MA, this is mass MB, and this has a velocity U B1, right? I can write the velocity in the center of mass reference frame. Okay, UA1 will then be VA1. This is the velocity of A in the original frame of reference minus V center of mass, right? And UB1 is equal to VB1 minus V center of mass. Okay, so once I find the center of mass, I can transform the velocities into the center of mass coordinate system, right? And once I have transferred the center of mass, we know that the velocity of the center of mass in the center of mass frame of reference is 0. So we know that U center of mass, okay, is equal to, this is the center of mass in the center of mass reference frame. Right? So in the center of mass reference frame, in the original reference frame, this was the velocity. In the center of mass reference frame, okay, where we have chosen the 0, the velocity in the center of mass reference frame, okay, the velocity of the center of mass is 0. So what happens? This times 0 is 0. So what do you get? You get MA UA1 is equal to minus MB UB1. Okay, so the momenta are equal and opposite, and hence after collision, right, because momentum is conserved, the momenta after collision should also be equal and opposite. So MA UA2, right, should reverse, right, should be equal to minus MB UB2, right? Because the momentum is conserved. The total momentum before is 0, the total momentum after is also 0, right? And not only that, the velocities in the center of mass, the velocities will reverse, okay? So, and once we have that, once we get these numbers, we can go back and transform, find the velocities in the original center of mass. Okay? So let me explain that by going back to our original problem. Remember, you had a mass of 4 kilograms and this was moving at 6 meters per second. And this was a mass of 2 kilograms moving at 3 meters per second, right? And it collided, these two collided, and after collision, we wanted to find this, and we wanted to find, so this is A, this is B, and we wanted to find, right? And we did this problem, and we found that one had a velocity of 7 VA1. We found that this had a velocity of 7 meters per second, and one had a velocity of 4 meters per second. So we found that this was 4 meters per second, and then this was 7 meters per second. Let's see if we can solve the problem. And the center of mass reference frame simplifies this problem, makes it easier to solve. So let's see how we go about doing that, okay, how we come up with the same two numbers. So the very first thing, we are going to find the velocity of this in the center of mass system. So UA1 is equal to, okay, VA1, this is VA1, this is VB1, right, minus V center of mass, and UA2 is equal to UB1 is equal to VB1 minus V center of mass. Okay. So how do you find V center of mass? V center of mass for this problem, so this is the velocity of the center of mass in the original coordinate system. So what do you get? MAVA1 plus MBVB1 over MA plus MB, right? So MAVA1, 6 times 4 is 24 kilogram meters per second, plus 2 times 3, 6 kilogram meters per second, divided by 4 plus 2, which is 6 kilograms, okay? Which is, this is 30 divided by 6, which is 5. So this, the answer is 5 meters per second, okay? So I can find UA1. What is UA1? It is 6 meters per second minus 5 meters per second. This is 1 meter per second, okay? What is the velocity of this in the center of mass coordinate system? It's going to be 6 meters per second minus 3 meters per second, and this is 3 meters per second. I'm sorry, I take that back. What am I doing? So VB1 is 3 meters per second minus, right, 5 meters per second. So this becomes minus 2 meters per second. So in the center of mass coordinate system, so I'm going to write this in the center of mass coordinate system, okay, you have two objects, 4 kilograms, moving at 1 meter per second, and this, which is 2 kilograms, moving, so this moves that way, and that moves at 2 meters per second in the negative direction, because that's minus, right? After they collide, the speeds will reverse, they will switch, all right? So U, okay, A2, okay, will become minus 1 meter per second, all right? And U, B2, will become plus 2. In other words, after they collide, in the center of mass coordinate system, this will become 1 meter per second, but that way. And this, okay, that's what I meant. Problems are simplified in the center of mass system. Now, as a homework, try to show that these numbers will switch, right? See if you can do that, right? So once I have that, so this is -1, this is 2. Now I can find the velocity in the original coordinate system. The original coordinate system, okay, I want to find UA2, which if I know that UA2 is equal to VA2 minus V center of mass, or VA2. That's the number I want to find, is equal to UA2 plus V center of mass. So you're doing the opposite. So UA2, that's that. This is UA1. This is UB1. This is UA2. This is UB2. Okay, so UA2 is -1 meter per second. And we found the velocity of the center of mass in the old coordinate system, okay, in the original coordinate system is 5. So what do you get? 4 meters per second, which is the correct answer, right? And what is the velocity? Okay, it'll be U B2 plus, right? And this was, I believe, -2 meters per second, or it was +2, right? It switched. So this became minus and that became plus. And this is 5 meters per second. And so we get 7 meters per second, which is the correct answer in the original center of mass system. Okay, so the velocity before collision, okay, and this is the velocity after collision. These two numbers are in the center of mass reference frame. These numbers are in the original, the velocities as seen in the original reference frame. And you can see that the whole problem becomes much simpler when we shift to the center of mass coordinate system. So that completes this chapter.